Hello? Hello? Quick test. Hey, all right, let's jump right in. What is computational modeling? Here we are in a course called Computational Modeling of Cognitive Processes. It's good to start with the first questions of what the heck are those two concepts. So, let's start with a bit of a basic version of this first. What's a model exactly? This might sound rudimentary to some of you, but honestly, this is one of those things that did not come together for me until grad school. So, fundamentally, a model is anything that is a reduced representation of something else, a more complex reality. So, think about a toy train, right? It's got a lot of the same features that a real train does, right? Usually some sort of engine, a caboose, a few cars in between. It's got the smokestack, that iconic bit. And sometimes they even have that little, like, neat wheel rotator arm thing. This one doesn't, but we would never call that a real train, probably. No one would, right? It's not an actual train. But why did we do it at all then? What's the point of it? Why make a toy train? Think about it through a child's eyes. Without this like reduced representation of a train that we've made here and set in front of them, right? They wouldn't be able to do a whole lot of interesting things that they do when they're playing, right? So they wouldn't be able to explore the train's features and how they relate to each other. Like, oh, there's wheels. Oh, there's 3 wheels on each side of this one. Whatever, right? They wouldn't be able to ask questions about the train and its parts. They would have to go and see a real train to do that, which is fine. That's cool for the kid if they're into trains, but they wouldn't be able to do it in an environment that's accessible and wieldy to them. I mean, they're little. They sit on the floor, right? And they also wouldn't be able to make predictions about what it would be like to ride in that train, or what it might be like to be a train conductor, or any other mode of play that they're going to adopt, right? They're doing all these things that are fundamentally, when you think about them in a broader sense, pretty useful, even though it's just play, you know? So, sure, the kid is just having fun with this little train, but they're also learning about a huge, complex piece of transportation infrastructure, machinery, right? That all thanks to this little model that they're playing with, this toy version. These are both mid-journey approximations of trains. So here's the approximation of a real train and a toy train. They came out too close together. I should have messed with the prompts a little more. You'll probably see more of that art in these as the course progresses, because screw it, it's wild. What a strange world. Okay, so let's continue on other things that are models. What is this? I ask you, the viewer of a video that knows, and we both know that you can't answer me, but what is this? It's New York, right? It's the state of New York. It's a map of New York State. This is not New York, right? We're standing on that. We're surrounded by New York. We live in it. But this is still a representation of New York. It's a model of New York. It is a reduced form that is somehow useful. It models interesting and useful parts of New York. It shows us where all of the bodies of water are. It shows us where all the roads and many of the cities are. It shows us where even some of the, elevations a little bit kind of here. But if I asked you this, where are the birds? Right? You can look outside and see birds. It's freaking goose season, right? There's no birds here. Birds are a part of New York, for sure, especially as we go, but there's no birds on this map. That's the idea. This map is a reduced form that we use for stuff. We use it to make all kinds of interesting decisions in our lives, like where should I go? How far is it? So maps are models, right? They represent land, but then in this like super reduced form. They simplify and generalize concepts that are a little bit too unwieldy on their own, and then they help us navigate the world in specific ways. And in science, they help us make certain predictions. So, okay, so continuing this, maps with roads and cities help us plan driving routes. Maps with water and elevation represented help us get a better understanding of, like, geography, right? What are the structures of this place? Not just a flat overhead view, right? Major landmarks might help you get a better understanding of the history of the region. Let's keep adding to this. So this is the standard map you get on Google. I've just added the terrain now. Look at this. We used to have this, like, kind of vague impression of height, but hey, buddy, them's the Adirondacks right there. This sort of bubbling high mass of mountains. We can now see them very clearly. You could now start to make decisions about, like, oh, if I'm going to go hiking up a mountain, well, that's the region I would want to be in, right? Further, we can just make it the satellite image. You can just have it be the literal light pixels that are available from a satellite at this height. Obviously, we all know you can zoom in on Google Maps and all that stuff, right? Which, it gets us closer, right? This is like a photorealistic photo of New York now, but it's still just a model, right? It's not hundreds of miles wide. It's the size of your monitor. It's not like richly detailed. It's still just like, 10,000 pixels on this screen. So that's the idea of a map as a model. Other models, right? So that, I think we've kind of pinned down the concept of models broadly. Let's get more into how you use models in a scientific capacity. And we'll start with the simplest model in the world in terms of, like, statistics and such: averages. Let's say you're trying to answer this question: how much do humans weigh? The only true answer to that question is you have to weigh every human on the planet and figure it out, right? But we have something in our toolbox that we use kind of all the time. You don't need to know every human's weight to get a useful prediction about what human weights are likely to be, right? So by looking at a sample of humans and computing their average weight, we can get a solid idea of how much most humans weigh. This is just a fully abstracted thing, but imagine this is the data set in the world. We can draw a single line through it. This single line, this horizontal line, is a representation of the entire data set, right? It's a reduced form of all of the other actual data points. It's pretty much the simplest model possible. It's a single number that represents some feature of all humans on Earth, or at least all the humans that we measured. There's a lot of assumptions baked into further stats, but this is a simple model. So what's the deal with this, with averages then? They are not real, right? They are a computed abstraction. They are a simplified model. Just like a toy train is not a real train. Just like a map is not New York State. Averages are wrong, right? There is no human who literally weighs the exact human average, because if you compute the human average out to several decimal points, then no human will ever be the exact amount. I know that's silly, but, like, that's kind of the point here. It must be wrong. It's necessarily wrong to reduce, because if it wasn't reduced, it would just be the real thing, right? So the idea is there can be huge margins of error between the average and what one human actually weighs. No one person is the true average. But averages are still super useful, right? They tell us what a realistic answer might look like. We can now know, oh, humans are probably not going to be 7,000 pounds. And they're also probably not going to be 4 pounds. That wouldn't make a lot of sense, given that the average seems to be in, I actually forget, it's like 150 or something. I don't know. Pounds, if you're from a different weight system. So yeah, they're super useful. They give us a picture of what a realistic answer looks like. And you can use it to make predictions, right? Maximum occupancy on a plane or an elevator, right? So you walk into any elevator, there's some kind of plaque on there that says this thing's rated for 10 people or 4,000 pounds or whatever it is. Usually that people numbers a little lower than they need, just to sort of give people like, hey, don't overcrowd this thing. You don't want to risk it. Or the design of a desk chair, right? Or a car seat. If you're designing a car seat or a desk chair, you need to consider both dimensions. So like a larger person might be unable to use such a chair, or like a smaller person might, if the lowest height of the chair is a little too high, it gets strange, right? So designing something around the average, it's not the only thing you should do when you're designing. Most chairs need to be a little bit modular so they can accommodate more people, but the average still factors, right? It's still a piece of the puzzle when you sit there to try and design this chair. So this is we've already kind of gotten into it, but this brings us to that critical piece of understanding for all of modeling and this entire course. All models are wrong, some are useful. It's a kind of a truism said by George Box. It's kind of what we've already gotten into. Inherently, when you reduce something to a representative form that is smaller, aka a model, then something is lost, right? You no longer have a lot of the data, right? The map couldn't be useful if it had to be the size of New York State, right? But in shrinking the map down, you lose every tree, every bird, every, human being living their life, right? Not saying that we should capture all that, but we're not capturing all that in a map. So let's keep moving this train forward to, we talked about the simplest statistical average model being the average. You can also ramp up the complexity. So you can make your model less wrong by increasing the complexity and adding more variables than just your average that represents the whole population. So for example, if we're still trying to determine somebody's weight, the simplest model is to just say, they're probably 150 pounds. Just like slapping the average weight onto them and rolling with it. But if you want to be a little more robust with your modeling, you can add other variables that help to predict weight as well. So if we happen to know their height, for example, then we could say, how far do they deviate from the mean height? And, if we've also computed something like, how many pounds are added per inch of height. It's an average thing. Again, we're doing averages of averages here, but now we have this capacity to much better predict somebody's weight if we know their height using this model. This model now includes height as a factor. This is where linear regression models come into play. You start adding more terms, you get a more and more degrees of freedom for your model to use to fit the actual data and make useful predictions. Although add too many and it starts to overfit as well, but we're not focused on that right now. That might come up later. So with this model, we know the average weight and height, and if we can measure their height, we can make a much stronger prediction about their weight, right? You can continue to make this more and more complex. Add their weekly calorie consumption, because that's certainly going to be a determinant of weight. Add all their known genetic conditions, because that'll be a determinant of their weight. Add their resting metabolic rate. Add their anything that you can figure out about how they live and how they exist in their physical form, and you'll have a better and better chance of doing a good prediction on what their weight is, right? You'll never quite capture 100% with any model. Again, they're all wrong. But the more complexity you add, the better it can predict the unknown bits. So, yeah, you see, weight can be just average height. You add more complexity, so height difference by pounds per inch. You might recognize this as another variable input then times the scalar, right? So y equals mx plus b, that kind of stuff. And then adding another term, right? Caloric difference per pounds per week, blah, 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 So you can extend your mathematical modeling as far into the ether as you like. Now, math models like this have limitations. They're great for predicting things that are simple, observable quantities, right? Because all it's really doing is mapping one set of input numbers onto an expected output number. great. I mean, when it works, that's fantastic. How much does something weigh? How much is it going to cost me? How long will it take to get between point A and point B? These are all like useful quantities that we can use these kinds of mathematical models on, statistical models on. They're closed form, which is super cool. It means you can solve for a specific answer in a single step, right? You as long as you compute the equation, boom, we're through it. You can plug the variables in and get a single specific answer that is your prediction, right? Like we were talking about, we can predict the person's weight without knowing it more and more, the more you add into the equation. But here's the problem. Some things can't be solved with a unified equation like this. This is where we reach the limitations of math modeling. Consider a droplet of water. How do you predict the behavior of a single drop of water, right? I'm going to go back real quick just to reference this. I should have put it on the next slide probably. So you can think about gravity, right? We have, most of us have learned a little bit of that physics stuff. Your velocity downward is, you're always accelerating downward at 9.8 meters per second squared, right? So drop a ball, it falls 9.8 meters in the first second, it falls 19.6 in the second, 29.4 in the third, blah, 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 until it speeds up. Eventually it does hit, what do you call it? Terminal velocity, but it's usually pretty good, right? This is a fair approximation of how gravity functions on Earth. But that's the starting point of a droplet, right? So we've got that factored in. We've got, okay, well, I can give a rough estimate of how far it's going to fall over time. But then you got to add air resistance. Then you got to add the effects of the water surface tension. What about its viscosity? What about its temperature, its salinity? All of these things will affect how it moves in the world. And you know what I didn't even mention on the slide? It also, not all water droplets fall. Some of them just live in clouds. Gravity doesn't do anything to that. Why? What do we do? How do I predict the movement of this water droplet? The fact is, even with all of this, even if we had, every variable possible, down to the quarks and bosons, it still only predicts what happens to that droplet in a vacuum, right? These are equations that have no middle state. There is no step-by-step. It is just, well, if I want to know where the droplet will be in an hour, so let me do some computations. Well, computations is the correct route. Flash forward. But it's more like, let me solve the equation and just know the answer. Here's the trick. Every perturbation, every tiny change in the environment that this water droplet encounters is going to change how the droplet behaves. It's going to change the outcome. It's not just going to change the next step, but it's also going to change the entire destination. Quick aside, stupid, lazy adult crap, but not lazy, but stupid adult crap. If you ever bought a house, or if you know anybody who's ever bought a house, you get your amortization table right as soon as you start doing the mortgage. And once it's all like settled, they're like, this is the list of all the things that you will pay over the course of the entire time you are paying off the mortgage. It's like your full 15 or 30 year list of payments that you're going to make. They say this is a stupid list because if you ever pay a cent more than what the number is for a month, say 1 month you got a windfall and you want to drop $1,000 into your mortgage, all those numbers are garbage now because they've all been offset by this calculation. They're going to have to recompute all of your interest and all your stuff, and your payment will go down ever so slightly. That kind of captures the same idea here. It captures the idea of this is, you can't just have a frozen form of something and expect it to work properly when other things can enter the mix. This is the fundamentals of chaos. So chaos it has a reputation in the way that people talk about it. They think, oh, chaos and evil and boring, like tedious, right? That's not what chaos actually means in a scientific sense, in an information theory sense. Chaos is this concept that things are all interacting with each other all the time. It is a huge chaotic blitz. Every inch of creation is full of energy that is moving around, right? Including you and me, including all the computers you're touching right now and all the airflow in your room. Everything is part of chaotic systems, right? So where various other entities and systems are constantly interacting with each other. The behavior of a droplet is subject to the behavior of everything else in the physical world, constantly, for as long as it exists. This is where that butterfly effect stuff comes from. I think people oversell the, oh, a butterfly flaps its wings and it creates a hurricane. No, a butterfly flaps its wings and it contributes to all other action in all other particles near it, and those become also enmeshed with their nearby particles. So yeah, technically the butterfly eventually affects a hurricane, but really it's more like every action has domino effects to everything around you. So this is a basic property of chaotic systems. They're highly sensitive to initial conditions. So, you know, if you don't know all of the conditions when you're trying to make one of your closed form predictions, then you're already short. You're a day late and a dollar short. They're also highly sensitive to these perturbations, right? So every, like I said about the amortization table, every time something is slightly changed or knocked loose, all of the rest of the predictions you were going to make sort of become larger and larger errors, right? So the example here, and I have a video, hoping it loads properly. Try dropping a ball on a windy day. Does it drop straight to the ground as the gravity equation predicts? Or does something else happen to it? Now this isn't the exact same thing, but this is some weird, this is some weird stuff. I love this video. Let's see if it does it and if it starts at the right time frame. They're gonna drop this basketball off a dam and they're gonna give it a little bit of a spin. Now, in a vacuum, this ball would just fall straight down as normal. But this ball is interacting.
Whoa, look at that go!
as it speeds through reality, as it goes through the dam. It didn't just drop to the ground. The airflow was not trivial. The airflow was not something that you just sort of write off, right? So that's the concept. So continuing this on, you know, another example is how we model weather patterns, right? If we can barely hope to predict how a single droplet moves through this crazy world, how can we hope to predict weather, which is like a billion, trillion, quintillion droplets of water? And the answer is computational modeling and simulation. Hey, we've arrived. So rather than trying to solve for a specific outcome, right? It's just a specific number you're trying to compute at the end step, right? Instead, we're trying to simulate the moment-to-moment behavior of weather systems, right? So what is likely to happen next based on a whole bunch of principles we understand, I forgot to include on the slide, and what has happened recently, right? So weather modeling does this by breaking the world into these grids of cells. So it's like a grid around the Earth and then like cells of like air pockets through the atmosphere, right? And you're trying to simulate the behavior of each cell based on both its current history. So like, what are its properties? Is it high temperature, low temperature? How's the barometric pressure? But also those of its neighbors. How's the barometric pressure a mile away? And if you get enough data, you train enough systems, you write enough things that can do a lot of these small scale maths that we've been talking about, math modeling for individual cells, well, now you can kind of string them together in this interrelated, interconnected, complex simulation. So you have all these cells and you can just go one step at a time, right? You can go from, okay, time A, what are all the states? Now, each cell, if you say, hey, high pressure cell, if there's a super low pressure cell next to you, we think that represents a storm front. We're going to increase the probability of our predictions for things like rain or even tornadoes, right? This is why everything is done with percentage probabilities. These are things that, based on the history and the current conditions of things at you and nearby you, I can step forward through time until I arrive at, hey, I think it might rain pretty bad today. Not really true of the lake. Lake effect is a kind of a hot mess, but yeah, welcome to Oswego. So yeah, we're still using mathematical models, right? But we're still using like, okay, well, what's likely to happen based on where I'm currently at? But we don't try to solve for the final destination. We try to simulate forward towards some potential future. So that brings us to the overall idea of computational modeling. We have arrived at the concept. We aren't just attempting to predict the outcome of a single variable. We're trying, at a given time frame, we're trying to generate behavior that is similar to the behavior of the real system we're looking at. This approach allows us to model complex systems, right, that are super chaotic and nonlinear and filled with things that interact with each other, not just hoping that they don't. You know, a classic physics equation always assumes the chicken is a sphere and assumes that you're in a vacuum. Reality, chickens aren't spheres and air is everywhere. So, complex systems that are chaotic and nonlinear, filled with things that are all interact with each other. Why does that sound familiar? Aha! Computational modeling and cognitive processes. So, cognitive processes, which go to the other lecture, are shining examples of complex systems. You know, every behavior is the result of a network of interacting neurons, at least, not let alone all the other things that are happening in your body, in the outside world, in the chaotic storm of maybe you're in a bad mood, so things up here are affecting things like what you say to people. Whoops. So we're subject to these perturbations from the whole environment, from our own bodies, from our own internal processes. And that's a prime example of a complex system, which is why we need computational modeling to approach trying to understand it. So this is not to suggest that there's no value in modeling some of the more predictable bits of cognition. For example, memory decay is one of those simple things, like our forgetting rate. How long does it take us to forget simple crap? Like, oh, I made you memorize a list of words, and oh, it took me an hour and a half to forget what most of them were, or whatever. Those are actually pretty simple math equations, but they're still pretty useful, right? And they can become part of more complex simulations. That's kind of the core. You'll see that in the next lecture. So just always remember, it's still wrong. Memory decay rates as a simple math model, especially alone, it's very wrong. Just like an average is very wrong, but it's still useful. So we take this computational approach to cognition, and that's what this course is all about. All right.